It is very important when testing certain and specific things within an environment to ensure that you use all the right equipment, which is guaranteed to be the most accurate and reliable during your data collection. One of the things that we tested was the vertical jump. Ideally, this should take place in a lab environment where force plates are used. Force plates are embedded into the floor of the lab, and to use them you have to stand on them. When you make contact with the force plate, they match and equalise your force to measure your ground reaction force. Force plates are able to record 1,000 measurements per second, which means that your result that you receive is really detailed and informative. The force that is applied through you to the ground is always matched equally but oppositely, allowing the force plates to take a very reliable reading of everything that is going on in the seconds that you jump. When you first step onto the force plate, it is important for you to calibrate the equipment. Once this is done, this is where we see force plates becoming very accurate. On a graph which is presented at the end of the jump, you are able to see each stage of the jump and how the forces change at each point. For example, as you bend down and prepare to jump by bending your knees, we would expect to see a decrease in force against the force plate. As you are doing so, you are pushing down more, which causes you to change direction and move upwards. As you take off, there is less force again because you are making very little contact with the ground. However, when you land, the force plates would record a surge in forces because all your weight is suddenly being put back onto the force plate, making it increase rapidly. Force plates can give a lot of readings per second. If your jump took an overall time of 3 seconds, the force plate is able to break down your jump into half a second each time, which gives a very detailed overview of your motion and forces at different points of the jump. Force plates not only can give you the force in your jump, but they also give you the height that you have jumped and the velocity of it too. This makes them the best and most accurate way to measure a vertical jump. The other test I focus on, which is an ideal way of running it, is a 20-metre sprint. Ideally, when measuring someone's speed on a 20-metre sprint, you would use high-quality motion cameras. Videoing someone's performance allows us to watch the clips back and use specialist software such as Dartfish to analyse the performance. For example, you may play it and slow down the video down to look at the angles of someone's elbow when shooting in basketball to see if they match or are similar to the perfect model that you have created. In terms of the 20-metre sprint, the ideal way to record each split time of the sprint would be to use camera footage and software. The type of camera which would be the most ideal to use would be something called a Vicon camera. This is a 3D camera which allows you to see a 360-degree view of the participant whilst they are sprinting. This makes the data collection very accurate because you'll be able to have the right perception level at each 5-metre point of the 20-metre sprint, which means that you can accurately split a time when the runner hits the 5-metre markers. To use the Vicon cameras, you have to place markers on specific parts of the body. In this case, you would need them on the arms and the legs. The sprint would take place in a lab where anything more than 6 cameras would be placed around the room to get the 365-degree of the action. The cameras are able to generate a 3D model of the athlete, which you would upload onto a software such as Dartfish or Quintet to analyse the person's performance. Camera placement is also very important, therefore, when looking at the ideal way to run this test, you would ideally think about your camera placement, triangulation, tilt, roll and pan. However, if you're using a Vicon camera instead of a 2D camera like we had to, these sorts of things will usually be done automatically, as the 3D cameras are set to automatically track an athlete once they create the motion. Another way which would have been ideal to use when recording the 20-metre sprint would have been to use light gates. These are positioned to intervals on the sprint such as 5, 10 and 15 metres, and then they are automatically record the time that someone passes through them, making them very accurate and reliable when you are trying to record and analyse someone who is moving quickly. However, these would only be used in a lab environment or a professional environment, as they are very expensive and advanced, which means that you need good knowledge and lots of experience as to how they work to get the full potential out of them. Also, in an ideal environment, we would look to capture the vertical jump in video. The best way to do this would be to use a Vicon camera set up in a biomechanics lab. However, in a lab you can also use a 2D camera set up as long as you work to place the camera properly and set it up correctly. When setting up a 2D camera, it is important to consider things such as the camera's settings, such as whether the shutter speed is not going to make the image blurry. This means that you need to think about how fast or how slow the camera shutter needs to open and close to make sure that you get clear images and videos. Furthermore, you also ideally need to know how many frames the camera will take and how quickly it will do this. It is also important to consider lighting when thinking about your shutter speed and your frames captured. It is important that you are able to see the participant clearly. If you have a fast shutter speed on, light has less time to get into the frame, which can cause the image to be dark and hard to decipher any analysis from it. You also ideally need to line the camera up a good distance away from the participant so that their whole jump is captured in the frame. This is called the field of view. And lastly, for the camera setup to be most ideal, you must consider the placement of it in terms of triangulation, where your camera should be placed in a triangle relevant to point 3, 4 and 5 of the subject when they move. The placement of the camera depends on what type of motion you are looking to film, such as the participant is moving or not. Ideally, you should be perpendicular to the participant so that you can capture all the angles which you may need to use later on in your analysis. To set up your camera position, it must be done very methodically. When filming the 20-metre sprint, you must set up the camera perpendicular to each light gate to match a straight line plane at which they are running at. This is where the 3, 4 and 5 rule comes in. However, when recording the vertical jump, it is important to consider the tilt of the camera. This means that the spirit level must be equal so that you aren't recording on a slant. Furthermore, you must make sure that the camera is level and not edging towards the left or the right. The camera shouldn't be biased to one side. Lastly, to make the situation most ideal and to make the results clear and accurate, you must be able to pan the camera so you can record every bit of movement. Usually this is best done on a tripod where you won't change any other factors in the setup of the camera. Overall, to get the best footage of the movement, you must make sure that you're using a high quality camera that can capture lots of frames per second like the force plates do in the lab. When preparing to do tests within a biomechanics lab, it's important to be aware of perspective error. The perspective that you're looking at something can change how it appears to you. This means that when recording the sprint, they may appear to cross the line when actually they haven't yet, or they'd already crossed it, which will make your results inaccurate. Therefore, in the lab, the people running the test would use cameras at every point when recording the test to ensure that all the angles of the run are recorded at the correct point each time.